In this video, we will discuss about principal stresses. So first we discuss about normal stress and shear stress on our element. So here, if you see, this black color is our element which we are analyzing. And now this element is taken from our work specimen at any particular point. And these are the stresses which are acting on it. So sigma x is on these two parallel plane, which is in tensile. By default, tensile is considered as positive, and sigma y is on the perpendicular plane. So this black color is a small element. Let's say this is our work specimen, and anywhere if we take a small element which is plane, so let's say here if we take this element, and what are the stresses acting on this particular element in different directions we are drawing. So here sigma x is acting in this plane, sigma y is acting on perpendicular plane. Now the shear stress is acting, you see here, these are the shear stress, and the opposite two are the complementary, because these two shear stress are giving, let's say I hold this and I pull this surface down, so there will be shear stress here and here, because I am giving a stress. But to maintain this particular element in equilibrium, the material will generate internal stress in opposite direction like this. So if I try to rotate this element like in this clockwise direction, the anti-clockwise stresses will be generated inside the material, which are called as complementary shear stress. And this is the stress denotion of our this black element. Now let's say we know these values, all the stresses, and I want to find stress at this particular plane. So here sigma x, sigma y and tau is acting, but we don't know where it is acting maximum. The combination of these stresses can act maximum on this plane or any other angle, means at any other plane. We don't know that, we just know these values. Now to calculate that maximum stress, first we have to define what will be the stress at this particular angle. So now I'm drawing a free body diagram of one half of this plane. So this is the free body diagram, and here if you see, sigma x is acting here, sigma y downward, means on this plane. So each particular stress is acting on one particular plane. So this sigma x is on this plane, sigma y is on this plane. This shear stress here acting on this plane, and on the bottom plane there is a similar shear stress. So there is a tau xy which is acting on these planes. Now we have cut from here. So to balance this particular section, there will be internal stress developed. We denoted it by sigma n, which is a normal stress acting on this plane due to these stresses, and to balance these stresses, and shear stress on this plane is acting in this direction. Theta is the angle. We are finding a generalized equation of stresses at particular angle theta from sigma x plane. Now from if we balance these particular stresses by multiplying it in the area and balance the forces, and then finally finding these two values, we will get these two equations, sigma n and tau s. Sigma n is normal stress acting on this particular plane which is at angle theta. So here we have sigma x, sigma y, again sigma x, sigma y, cos 2 theta. Theta is the angle of plane from this sigma x plane, and tau xy and again theta. So from these three variables and theta, we are finding normal stress sigma n at any particular angle. If we put value of this sigma x, sigma y and theta and tau xy, we get the normal stress on that particular plane. And tau xy similarly we can calculate from this equation. We have similar variables here, but the different different signs and functions. So here sine 2 theta, cos 2 theta, sigma x, sigma y. So these are the two equations which we can find these two stresses on any plane by simply varying the theta, and we know value of sigma x, sigma y. So these are the normal and shear stresses. Now we will look at the complementary stress. So here if you see, sigma x, sigma y, both are acting on our element. If we rotate it by some angle, this green color I have rotated it, this black color I have rotated, and we got this green color. Now let us assume that sigma n normal is acting on this surface, and at perpendicular surface sigma n dash is acting. So if we take summation of sigma x sigma y, then that will be equal to sigma n plus sigma n dash, means the complementary shear stresses which are at perpendicular angles. If we do the sum, it will remain. If we rotate our element or at all the angles, this particular complementary stresses will be having equal value of summation. So sigma n plus sigma n dash will be equal to sigma x plus sigma y. So at any angle, if we do summation of perpendicular stresses, that will be equal, and they are at 90 degree and called as complementary stresses. So sigma n is at any random angle, and perpendicular, if we take from sigma n, we get sigma n dash, and if we do the sum, that will be equal, always equal to sigma x plus sigma y. If we do same for tau s at 0 degree plus tau s at 90 degree, that will be equal to 0. This 0 degree is at any particular angle. If we take 0 degree and take tau s at 90 degree from that particular angle, let's say I have taken shear stress at this particular angle. So here this particular value and the perpendicular shear stresses, if we do the sum, that will be equal to 0. Now let us look at the principal stresses. So principal stresses are stresses which are maximum, and it is at some particular angle. So principal stresses are sigma 1 and sigma 2, and they are calculated from this sigma x, sigma y, and tau xy, like this. So this is the equation to calculate the maximum value of stress. They are called as principal stresses. Sigma 1 is major principal stress, it is higher value. Sigma 2 is minor principal stress, and sigma 1 and sigma 2 are also complementary, means they are at 90 degree, and this plus sign is used to calculate sigma 1 and minus sign is used to calculate sigma 2. So here plus minus means we get two equations, and we have to find sigma 1 and sigma 2. Sigma 1 will be higher than sigma 2, so sigma 1 and sigma 2 are at 90 degree to each other. So these two are called as principal stresses, major and minor. And on this particular plane where sigma, all stresses are acting at particular plane, like sigma x is acting at this plane, sigma y is acting at this plane, similarly sigma 1. So here if you see, the sigma 1 will be acting at particular plane, sigma 2 will be acting at perpendicular plane to that plane, and these two planes are called as principal planes, and shear stress on principal planes will be 0. To find principal planes, we have to use this equation tan 2 theta p equal to tau xy upon sigma x minus sigma y divided by 2. So we call it as theta p1, which is principal plane 1, principal plane 2. Sigma 1 will be acting on principal plane 1, sigma 2 will be acting on principal plane 2. To find the maximum shear stress, so on one particular plane there will be maximum shear stress, and this maximum shear stress will be acting at theta s1 and theta s2. To calculate these two values, we have to use this equation. So on these particular planes at particular theta s1, theta s2, we will have maximum shear stress, and we have to calculate by this equation. Now on principal planes, shear stress will be 0, but on maximum shear stress there will be normal stress present. Normal stress at theta s1 and theta s2, which are these planes of maximum shear. We have normal stress, which is equal to summation of principal stresses divided by 2, so average of principal stresses. And this tau max is also calculated by sigma 1 minus sigma 2 divided by 2, which is called as in plane maximum shear stress. There is also absolute shear stress, which we will discuss further in future videos, but here the maximum shear stress which we are calculating is in plane shear stress, which is calculated by subtracting principal stresses divided by 2, and normal stress on that particular plane will be sigma 1 plus sigma 2 divided by 2. So if you do numericals on this, you will get better ideas, and these are very basic concepts, and it is also solved by Mohr circle, which is very convenient method to solve all this equation very quickly without using this equation. This is analytical method. There is one graphical method which is called as Mohr circle, which is much faster than this, but this is also useful because in some cases we cannot use graphical method. So thank you for watching this video, and see you in the next video.